Hey everyone, and welcome back. Today we're going to be taking a deep dive into something pretty awesome, bird flight.
Specifically raptors.
Yeah, raptors, the kings of the sky, you know.
How they make those really smooth turns.
Yeah, like how do they do that? We've got this really cool research article from Science Robotics.
It's a question that's puzzled scientists for a long time. We see birds twisting their tails all the time, but the mechanics of how that actually leads into a turn have been a bit of a mystery.
Yeah, so I mean, we know that the tail acts kind of like a rudder, right?
Mm-hmm.
It's preventing yaw, like that side-to-side motion.
Right.
But how does that twisting actually translate into banking into a turn? That's what this research was trying to figure out.
And they did it in a pretty ingenious way by building a bird-inspired drone.
Oh, wow.
They called it LisRaptor.
LisRaptor. That sounds pretty intense.
It's designed to mimic the wing and tail morphology of a hawk, even down to the structure of the feathers.
Wow, so they really went all out with this.
Yeah, and the reason they did that is that weight distribution and inertia play a huge role in how a bird moves through the air.
So to really understand how a bird turns,
Exactly.
you need a model that moves in a similar way.
Precisely.
Wow.
And LisRaptor is remarkably lifelike. It can fold its wings by 60%. Its tail by 68%, very similar to what you see in real raptors.
So this thing really moves like a bird.
Yeah.
That's amazing. What did they learn by studying LisRaptor?
Well, one of the first things they discovered through wind tunnel tests is that when LisRaptor twists its tail, it actually reduces lift, causing the nose to pitch upward.
Oh, interesting. So it's almost like the tail is acting like an elevator as well.
Yeah, you could say that. You see, traditional aircraft use their elevators to increase lift during a turn, but birds seem to be achieving this with just the tail twist. Much more efficient.
Yeah, and that means they don't need to make, like extra adjustments with their wings to maintain altitude during a turn. That's pretty cool.
Yeah.
Talk about a streamlined design. But how does this tail twist-induced pitch-up actually lead to a roll, which is what you need to bank into a turn?
That's where things get really fascinating. They use a technique called flow visualization to see how the air moves around LisRaptor during a turn.
Okay.
And what they found is that the twisted tail interacts with the wake coming off the wings.
Wait, hold on. What exactly is a wing wake?
Think of it like the trail left behind a boat as it moves through the water.
I gotcha.
It's essentially what a wing wake is, a disturbance in the air caused by the wing passing through it.
Okay, that makes sense. So the tail is affected by this wake.
Exactly. Because of the twisted position of the tail, one side gets pushed more than the other by the wing wake. This creates what's called asymmetric lift, meaning one wing generates more lift than the other. And that's what initiates the roll and allows the bird, or in this case LisRaptor, to bank into a turn.
So it's not just the tail itself, it's how it interacts with the airflow created by the wings that's key to this whole turning mechanism.
That's the aha moment of this research. Previous studies hadn't really considered this wing-wake interaction. LisRaptor was crucial to finally seeing the full picture.
That's remarkable, but they didn't stop there, did they?
No, they wanted to understand how this tail twist mechanism works at high speeds too. Think of a hawk darting through a forest, making sharp turns to avoid obstacles. So they cranked up the speed in the wind tunnel and put LisRaptor through its paces.
So what'd they find?
It turns out tail twist is just as important for high-speed maneuvers. In fact, they discovered that during sharp turns, birds combine tail twisting with a rapid pitch-up motion, almost like a brief stall.
Oh, so they're using the tail to both initiate the turn and control the pitch of the body. That's impressive.
And it gets even more nuanced.
Oh.
They also observed that real birds often use what's called asymmetric wing folding during these high-speed turns, meaning they fold one wing more than the other.
I'm trying to picture that in my head. So they're like using their wings and tail in perfect coordination to like execute these really tight turns.
And when they incorporated this asymmetric wing folding into LisRaptor's design, they found it led to even faster recovery times after a turn.
So there's like a whole symphony of movements happening here.
It's really quite remarkable.
But what's really remarkable is that birds are doing all of this with just one set of muscles controlling the tail.
That's right, and it's incredibly efficient. It seems that tail twisting is the key to both stability and agility in bird flight.
Whether they're soaring gracefully or like dodging obstacles at high speed.
Exactly.
It makes you wonder how much energy a bird saves using this method compared to like an airplane.
Right.
With its separate control surfaces for yaw, pitch, and roll.
Yeah, you've got a good point there. Think about it. Airplanes have to move multiple flaps and rudders, all requiring a lot of energy.
Right.
Birds, on the other hand, have evolved this elegant system where a single movement of the tail can achieve multiple outcomes.
It's a reminder that nature is often way ahead of us
Oh, absolutely.
when it comes to efficient design.
For sure.
But speaking of design, I can't help but think about the implications this research has for building better drones.
Absolutely. Imagine a drone that can maneuver with the agility of a hawk,
Right?
navigating tight spaces and changing direction quickly.
Yeah.
That would be a game changer for all sorts of applications.
Like search and rescue missions in like a dense forest or urban environments or even delivering packages in crowded cities.
Exactly. And beyond those practical applications, there's also the potential for scientific research.
Oh, yeah.
Imagine a drone that can mimic the flight patterns of birds
Cool.
to study their behavior in the wild or even track the movement of other animals.
It's like having a bird's eye view of the world.
Literally.
Literally. I have a question.
Yeah.
Earlier, you mentioned how important it was for LisRaptor to have a similar weight distribution and inertia.
Oh.
To a real bird, can you explain why those factors are so crucial?
Well, think about it this way. A bird's flight is all about constantly adjusting its body position, its wings and tail, in response to changes in airflow.
Right.
If the weight is off or the inertia is different, the drone wouldn't move in the same way.
I see.
And the results wouldn't accurately reflect how a real bird flies.
That makes sense. It's like trying to understand how a figure skater spins and jumps
Right.
without factoring in their body weight and how it shifts during their routine.
Exactly. And remember, the researchers also paid very close attention to the placement of the tail on LisRaptor.
Okay.
It's much closer to the wings than you would find on a traditional aircraft.
I hadn't thought about that. Why is that proximity so important?
It all goes back to that wing wake we talked about earlier. By positioning the tail closer to the wings, it maximizes the interaction with that airflow. This allows the bird, or in this case the drone, to make more efficient use of the lift generated by the wings.
It's like every detail has been fine-tuned over millions of years of evolution to achieve optimal performance.
Absolutely. And it's not just during turning maneuvers. Even when the tail isn't actively twisting, its proximity to the wings plays a big role in augmenting lift and reducing drag, making the bird's flight more efficient overall.
Amazing.
Yeah.
But getting back to the tail twist itself, you mentioned earlier that it causes the drone's or the bird's nose to pitch up. Why is that important again?
It's all about maintaining altitude during a turn. You see, when an airplane banks into a turn, some of its lift is redirected horizontally, which can cause it to lose altitude.
Right, and to compensate for that loss of lift, pilots pull back on the control stick, which raises the elevator and increases the angle of attack of the wings, generating more lift.
Exactly. And with birds, that nose-up pitch caused by the tail twist serves a similar purpose. It increases the angle of attack of the wings, generating that extra lift needed to counteract the lift loss during the turn. And they do all of this without needing any extra control inputs.
It's like they've got this incredible autopilot system built in, and the tail is the key. I have to say, this deep dive has really opened my eyes to the complexity and elegance of bird flight. You know, we've been watching birds soar for centuries, and yet we're still learning so much about how they do it.
It really highlights how much we can learn from nature. This research is a perfect example of what we call bio-inspired design, where we take inspiration from the natural world to solve engineering challenges and develop new technologies.
Like those super agile drones we were talking about.
Right.
The potential applications are truly exciting. But this research goes beyond just building better machines. It also raises some profound questions about our place in the natural world.
It's a humbling thought, isn't it?
Yeah.
That we can gain so much insight by simply observing and studying other species. And it makes you wonder what other secrets are waiting to be discovered and what innovations they might inspire. But before we get too far ahead of ourselves, perhaps it's time to bring our listener back to the key findings of this research.
That's a great idea.
Yeah.
We've covered a lot of ground today. So to recap, all right, so let's rewind here, make sure we've got all the tail twisting highlights.
Yeah.
First off, it's not just about, staying on course.
Right.
It's fundamental to how they turn at all speeds.
At all speeds, slow and fast.
And it's really that interaction between the tail and the wake.
Right, that twisted tail interacting with that wake coming off the wing.
Yeah, and creating that uneven lift, that roll moment, which was the missing piece of the puzzle for so long.
It really was.
And who knew that, like, nose-up pitch the tail causes
Right.
is so crucial. It's like their built-in system to avoid losing altitude
Right.
while they're banking.
Exactly like an airplane's elevator.
Yeah.
So much more streamlined.
Way more streamlined, nature's efficiency, right?
Excellent.
And don't forget those high-speed turns.
Yeah.
It's not just the tail twist.
Right.
It's combining it with that rapid pitch up almost like a controlled stall.
Right.
And the asymmetric wing folding for that super quick recovery.
It's amazing how much is happening
Yeah.
when a bird makes a turn like that.
All in just a split second. But the big takeaway for me is that one set of muscles
That's one set of muscles.
in the tail manages all of that.
Exactly.
Talk about a multi-purpose tool.
Absolutely. And, I mean, you were spot on about the drone design.
Yeah.
Imagine harnessing that efficiency
Right?
and agility in our flying machines.
Search and rescue package delivery.
Absurd.
Sensations in challenging environments.
Yeah.
So many possibilities.
Mm.
But something has been on my mind this whole time.
Oh, what's that?
What if we took this research
Yeah.
and we kind of flipped the script a little bit?
Yeah.
What if understanding bird flight could actually help us build robots for exploring other planets?
Ooh, now that's a really fascinating thought.
Taking bio-inspiration to a whole other level.
A whole other level.
I mean, we've already got drones on Mars, right?
Mhm.
But they're pretty limited in what they can do.
Well, that's because the Martian atmosphere is incredibly thin.
Yeah.
It's about 1% the density of Earth's. Wow. So, fixed-wing drones struggle to generate enough lift.
Okay.
And helicopters rely on that thicker air to push against their rotors.
So are you saying that bird-inspired drones with, the morphing wings and the tails
Potentially, yeah.
could be the key to, like, more agile exploration on Mars?
It's certainly a possibility.
Imagine like a drone soaring through Martian canyons, adjusting its wing shape
Right.
and tail twist to navigate that thin air and all the crazy winds.
It could reach places that are currently off limits for rovers
Yeah.
and even our current drones.
We could map out caves, search for signs of past life, even scout for future human settlements. It's like opening up a whole new frontier.
It really is.
I mean, from this deep dive, what I'm really taking away is that sometimes the answers to our toughest challenges
Yeah,
are right there in nature.
absolutely.
We just need to have the ingenuity to apply those lessons.
Beautifully put. And who knows what other animal behaviors
Right.
are waiting to be decoded? What innovations they might inspire. The future of robotics might be a lot more feathered and winged than we ever imagined.
I love that.
Yeah.
On that note, I think it's time to wrap up this episode. It's been a fascinating deep dive into bird flight robotics and even a glimpse into the future of space exploration.
Yes.
It's been awesome having you.
It's been a pleasure.
And to all of you listening out there, thanks for joining us on this journey. Until next time, keep exploring.